So, the last thing that we want to do here is address the aspect of what happens when you have a spherical particle in a channel flow. I have taken a channel flow, but a lot of the things that I am going to discuss today is going to carry over for all other kinds of flows that you may have. Now, if you remember the argument we had when we did this at Reynolds 0 is that there cannot be a cross stream motion or lateral migration or lift, whatever you say. That if there is a spherical particle kept in a channel flow using arguments of reversibility, you can basically start by assuming that it goes one way and then you do a reversibility of the pressure gradient, so it will move the other way, then you do a reflection and you arrive at a contradiction and you say that, oh, then it cannot migrate. And this obviously can also be argued if you were to think in terms of tensorial dependence. So, the linearity argument will actually give you that there will be no migration. So, now if you say that non-linearity is basically going to disrupt this, and non-linearity, as you know, is basically the fluid inertia which is responsible for the wake. So, when you have a flow field in Stokes flow, there will be a 4/2 symmetry in the flow structure. The sphere is an isotropic object, so there will be a 4/2 symmetry in the flow field. The disturbance flow field will be 4/2 symmetric. Whereas, when you do this with inertia, you will break that 4/2 symmetry, and breaking that 4/2 symmetry is going to actually lead to creation of lateral forces. So, one of the earliest calculations which was done was actually not even in a shear flow, it was in the context that there is a sphere that is translating and the sphere is also rotating. So, in a viscous fluid you have a translating sphere and you or the sphere have rotation. Now, at Reynolds 0 you know that drag is equal to minus 6 pi mu a u, and then there is a torque which is minus 8 pi mu a cube omega. Okay. When you allow for low Reynolds number, you are allowing for non-linearity, and we have done this again, right. We said as a translating sphere you do it separately. See, this was the idea of linear superposition. You do the translation problem separately, you do the rotation problem separately, and then you can combine the result, which means the total force and the total torque can be found by these independent problems. But the moment you do non-zero Reynolds or you include fluid inertia, you can now have a coupling between the two problems. So, in a sense you will manage to get a force which will be proportional to its translation and rotation, the cross product. This is not possible in Stokes flow because this is a nonlinear term, and if you argue this dimensionally, what should be the dimensional factor? If you just use dimensional analysis, there is a length A rho times u square. So, this is like u square by length, right. Omega is basically like velocity by length. So, u times omega is like velocity square by length. So, rho u square is a pressure scaling from inertia. So, this is like pressure by length. I need to multiply this with length cube in order to get a force. So, this will be rho a cube, and the prefactor turns out to be interestingly just pi. So, this was a calculation which was done by Rubino and Keller, and it basically gives you what is known as similar to what you think of as a Magnus force. Let me just check the sign once. One sec, I do not want to get the sign wrong. So, this would be the negative sign. So, if there is a translating object and it is spinning, it is basically going to experience a lateral force. Now, there were several others who then I mean there is a series of many who have looked into this later, which came from Safman. Safman's calculation was you take a shear flow, and he considered a simple shear as a specific example, and in a shear flow, if the particle velocity was not equal to the fluid velocity at the particle center, which means there was a slip, either the particle was going ahead of the fluid or the particle was lagging with the fluid. So, if there was a slip, then there was a lift that it experienced, which is what Safman did. So, some of these calculation obviously requires and as you will see when we develop this, requires a little bit of going through how the entire force is found. I will take up an approach which comes from Ho and Leal, I believe 1974, where an attempt was made in order to calculate what was the migration velocity or migration force for a particle in a channel flow. Now, a motivation for doing this study actually came from a set of experiments by Segre and Silberberg. Let me check the year, one sec. (1962). What Segre and Silberberg observed was you have a pipe flow experiments, you introduce particles uniformly over a cross section and they get transported in this pipe flow. What they observed that after a certain distance downstream, the particles went and accumulated at a specific radius. So, there was an uniform distribution of particle, they get transported down the pipe, and then after a certain length you find that these particles go and instead of remaining homogeneous, they go and collect at a certain radial location. That radial location was roughly around 2/3 of the pipe radius. Now, this is surprising, right, because this is going against what we argued from Stokes flow, that Stokes flow actually says that there should not be any cross stream migration. So, if all the particles were present in a cross section, wherever they are, they should remain on that particular streamline. Assuming it is dilute enough that they do not interact, all those spheres, they should stick to the streamline, they should not move across streamlines. So, this experiment is kind of what led to a lot of these studies that came up. So, Ho and Leal is what we will mostly focus on today. So, we will say that there is a background uniform flow, so sorry uniform flow, it is background shear flow, and we have a channel flow here in mind, and I am going to construct a coordinate system which is glued to the particle, and the particle is allowed to move with a velocity up along the x direction. So, up along the x direction and spin with an angular velocity omega p such that the force and the torque on the particle is 0. The drag force and the torque on the particle. So, you make the drag and torque go to 0, you make the particle is moving in this channel, right, and it is moving along the x direction, along the flow direction. So, it moves with a velocity up and rotates with an angular velocity omega p such that its drag and torque goes to 0. Now, if there was no wall, what would be up? If you did Stokes flow and there was no wall, what would be the value of up? there is a u infinity of x, it has to be force free. If it is Stokes flow, what should be up? U infinity at the particle set location, which I am saying 0 here because the origin is, anything else?
Minus a square by 6 fluxing direction.
Right, that is basically what gives me the force free criteria. Now obviously this is not an unbounded domain, there are walls in this problem, so that calculation is a little more complicated than that regarding what would be the velocity with which it should move. So now if I write down the governing equation and I will be non-dimensionalizing. So for non-dimensionalization I will be using a length scale which is the particle radius. I will use a velocity scale which will be the center line velocity into the particle radius by the width of the channel. Now why I am doing this? The reason I am doing this is a force free torque free particle. Okay, this is a neutrally buoyant, the other word would be this is a neutrally buoyant particle. So this particular particle is seeing a local shear flow. So the Reynolds number is dictated by the shear rate. It is the shear rate which is dictating the effect of the flow here at this scale. So when I am deciding a velocity scale, that is the local shear rate or an mean shear rate multiplied by the size of the particle. So across the particle it sees a velocity which is the mean shear rate multiplied by the characteristic length scale which is the particle size. Okay. And you will have a pressure scale which will be mu um by h. Reynolds number is, in this problem, the particle Reynolds number would be rho umah into a by mu. So this is a square nu into h. There is a channel Reynolds number which is rho h by mu or h by nu. So the particle Reynolds number is a square by h square into channel Reynolds number. So if I define a parameter which tells me how confined is this particle as the size of the sphere by the gap of the channel, then this becomes alpha square Reynolds of the channel. So these are all the parameters that are there in this particular problem basically when we set out doing the non-dimensionalization. So if I write down my governing equation for the fluid velocity, so this is the non-dimensional fluid velocity, the total fluid velocity, and up is the particle velocity. So this is basically a reference frame sitting on the particle. Now for this fluid velocity, the boundary condition at the particle is the rotation omega p cross r. The fluid velocity at the wall is up, and this is actually y is equal to 0 and alpha inverse, because if this is 1 then this would be 0 and this is 1 by alpha. Alpha is particle size by the channel width, and u is equal to u infinity minus up as x goes to plus or minus infinity. So, this is the fluid velocity, the total fluid velocity. Now, if I define a disturbance, because you are familiar with the disturbance that is created by the particle, the disturbance velocity and pressure fields, which is defined as u tilde, which is total velocity, minus u infinity plus up, because this is the disturbance as measured sitting on the particle, because the background flow in the particle reference frame is u infinity minus up, and the disturbance pressure is P tilde minus P infinity. Okay. So, I will write down the non-dimensional equations for the disturbance field, which is u infinity dot del u plus u dot del u infinity plus u dot del u equals del square u minus grad p. So, this is my steady Navier-Stokes equation. I am ignoring the unsteady effects that are there in the problem, which is a fair enough assumption to do at the regime of Reynolds that I am looking at, where the wake effects and everything would be a steady wake that we would see. The flow field is, the disturbance flow field is also incompressible. The boundary condition is a rigid body boundary condition for the disturbance minus u infinity. In the particle reference frame, the disturbance should basically have a boundary condition, which is omega p cross r plus up minus u infinity. U should be 0 at the walls, and u should also be 0 as you move infinitely far away from the particle. X plus or minus infinity means that I have moved away infinitely far away from the particle. Now, this is your full equation. The only approximation you have made in this is dropping the unsteady term. There is nothing that has, there is no other approximation here. This is your steady Navier-Stokes. Now, you can go and plug this into any numerical solver and solve this equation and compute the forces acting on the particle. Now, the idea is up is an unknown, omega p is an unknown, because your objective here is to find up and omega p such that the total streamwise force or the drag and the torque should be 0. So, when you do this numerically, what you need to do is you need to basically keep changing your up such that the streamwise force or the drag force vanishes. Similarly, you keep changing the angular velocity or the rotation rate such that the torque also vanishes. But then the thing that we are more interested in here is that would there be a force that is in the cross stream direction? Would you experience, as this is experiencing 0 drag and 0 torque, as it tries to move in this direction, you are making it move with a velocity such that it experiences 0 drag and torque. Will there be any force in the cross stream direction? Because that is at the heart of there being a migration. So, this again you can do it numerically. You can find your up, you can find your omega p such that it is 0 drag and 0 torque, and then you can check whether you experience any force in the lateral direction. Now, instead of doing this entirely numerically by solving this nonlinear equation, we will see that is it possible at small Reynolds, because we know that this physics is going to come up at small Reynolds, to do this in a semi-analytical manner. The final calculation might still be a numerical calculation, but can we stick to doing linear problems and compute the forces? So, for that what we will do is we will say that Reynolds based on the particle is small. So, the velocity field I am going to expand as a series in Reynolds number. And I am not only expanding velocity field, I am expanding pressure field, and I am also expanding the particle translation and rotation dynamics. How fast should it move along the streamwise direction? How rapidly should it rotate? I will basically be also calculating all these quantities. Now, when you see this kind of a series expansion in Reynolds, do you get reminded of something which was a bothersome thing earlier in earlier lectures? Does this lead to any issues anywhere? Did you see this at any earlier stage? So, let me just proceed a little bit more and then I will come back to this question. So, if I do this substitution and collect terms in Reynolds number, which means I collect the 0th order term, I get an equation which is del square u naught minus del p naught is equal to 0, divergence of u naught is equal to 0. The boundary condition is u naught will be u p of 0 plus omega p of 0 cross r minus u infinity on r equals 1, u naught is equal to 0 on channel walls and as x goes to plus or minus infinity. At first order in Reynolds, I am going to get an equation which is del square u1 minus del p1 is equal to u naught del u naught plus u infinity dot del u naught dot del u infinity, divergence of u1 is equal to 0, u1 is equal to u p1 plus omega p1 cross r on r equals 1, u1 of 0 on channel walls and as x goes to plus or minus infinity. So, I am just sticking to the 0th order problem and the order Reynolds problem. Have we looked at these equations in the past? This kind of an approach, did we try this out? What was the issue when we tried this out? So, in the settling problem, if you remember, when we tried this out, we did not do this explicitly. We said in the settling problem that this right hand side, what was the, in the settling problem, what was the order in R as you go far away for the right hand side? Because u naught in the settling problem, u naught is a constant plus 1 over r, which means a term like u naught dot del u naught, that kind of a term is order 1 over r square. And then we said if it is order 1 over r square, that means u1 should actually become only a function of angular coordinate, and this was at the heart of what we came to know as the Whitehead paradox. This was basically the starting point of the entire thing on Oseen's length scale, that you cannot just do this regular perturbation. You cannot do this kind of an exercise where you expand in Reynolds and expect inertia to be just a correction to the viscous problem. This is exactly what we said is problematic, and I am trying to do that right now. The reason why I am allowed to do this right now is, if you think of the Oseen length scale the Oseen length scale for the neutrally buoyant problem, if you remember, in non-dimensional units scales as REP to the power minus half. Now, if your Reynolds number is very small, such that the walls of the channel lie within the Oseen region, then you can do this exercise. So, this is based on the idea that the channel walls, because that argument of Whitehead paradox was in an unbounded domain. You were doing something which was where the fluid was completely unbounded, which is why you said, we drew this picture in the beginning of today's class, right. So, you said it was in some shear flow, and then beyond a distance that scales as 1 by square root Reynolds, you will have Stokes solution not be uniformly valid. You need to realize that inertia and viscous terms are equally important. But what if you have a channel which lies within the Oseen region? Then you do not have this challenge, right, then you do not have this kind of a problem, because now you are saying that the walls of the channel are lying within the Oseen region, which means a Stokes plus correction approach is not going to be problematic. So, that is what we are doing. So, effectively this is reliant on, all of this is possible with an assumption that alpha times Reynolds P to the power minus half is much larger than 1. 1 by square root Reynolds is the length scale, the Oseen length scale. Alpha is the non-dimensional distance where the channel wall is located. So, the channel wall is smaller than the Oseen length scale. That is the effective idea which you are saying here. If that is the case, if it lies within the Oseen region, I can do this regular perturbation, else I have to do something else. So, I am going to right now stick to this particular assumption, and then now if you see, by doing this regular perturbation, you have a Stokes flow problem, which is the classical homogeneous Stokes flow problem, and here you have an inhomogeneous Stokes flow. The right hand side here, I can write it as some body force, right. The entire RHS is a known quantity if you have solved the homogeneous Stokes flow problem, right. So, you have to solve a Stokes flow problem with that body force. Now, this can be done, but are we interested in finding this velocity field and this pressure field? Is that something that we are interested in, or we are interested in something else? What is the goal of this calculation? So, UP and omega p gives you the velocity along the flow direction, how much that is going to get corrected or how much that is going to change. But what is the main motivation of this exercise? Is there a lateral force? So, we really do not care, I mean, in terms of finding the velocity field, or at least finding u1. Finding u1 is not our objective is to find the lateral force. So, what we will do whenever you hit something like this, where your goal is not necessarily to find the velocity field, we take help of one of the most powerful methods in Low-Reynolds number flow, which is Lorentz reciprocal theorem. So, we will do two problems. The first problem is the order Reynolds calculation, which we are reluctant in solving in entirety, right. So, this is something we don't really want to do, but this is basically our desired problem. This is the inertial correction, and we are going to choose a test problem. The test problem is, in Stokes flow, I have a sphere which is moving perpendicular to the plate with unit velocity. So, u hat, if it is the velocity field in this problem, it is E y, because this is x, this is y on r equals 1. So, you have a spherical particle between two plates and it is moving with unit, this is non-dimensionalized obviously based on how you have done the other problem, it is moving with unit non-dimensional velocity perpendicular to the wall. So, for this problem there is a velocity field and there is a pressure field which I am adding as a hat here. So, sigma hat, the pressure field here is minus p hat delta plus 2 mu E hat. Now, if I write down divergence of, so this is basically the starting point of my reciprocal theorem, but this reciprocal theorem approach is a little more generalized than what we have done earlier in class, because in class, if you remember previously, what we did was, when the two problems were solutions of Stokes flow, homogeneous Stokes flow. Right now one of it is not a solution of homogeneous Stokes flow, it is a problem that is an inhomogeneous Stokes flow, right. So, when you apply this divergence theorem, this is going to be a surface integral of n dot sigma u1 minus n dot sigma 1 dot u hat ds. Now, if I say that the volume is the volume occupied by the fluid between the particle and the walls, and what is the value of this integral at the wall? Why is it 0? u1 and u hat, they are all 0 on the walls and far away. So, if you define a control surface that includes the wall and a distance at infinity on either side at plus minus x being infinity, then that goes to 0 there. So, effectively this will become the integral over this particle surface and with a negative sign, if I am defining the normal as being the normal into the fluid. Now, this volume integral I can write it as divergence of sigma hat dot u1 plus sigma hat dot del u1 minus divergence of sigma 1 dot u hat minus sigma 1 dot del u hat. U hat is a total velocity field in the test problem, dV. Now, here if I substitute for u1 on the particle surface, that is known, right. So, this becomes minus up1 dot sp sigma hat dot n ds minus sp omega p 1 cross r dot sigma hat n ds plus what is u hat on the particle surface in the test problem? It is the unit normal in the y direction. So, this becomes E y dot sigma 1 dot n ds. What is the direction of sigma hat dot n ds? The sphere is moving normal to the wall in Stokes flow. What would be integral sigma dot n ds in that test problem? It would also be in the same direction. In a Stokes flow problem, I have this object moving with unit velocity here. So, the force that it will experience will also be in the same direction. And what is the direction of UP1? UP is the velocity that it moves in the flow direction so that it experiences zero drag. So, UP0, UP1 all of them are going to be in the x direction or in the streamwise direction. So, this quantity will be 0, the dot product will be 0. Now, if you calculate also the torque in this problem, there will be no torque and it will also experience that contribution will also go to 0. What is divergence of sigma hat? Test problem is Stokes flow. So, divergence of sigma hat is 0. Now, this sigma hat dot del u1 and sigma 1 dot del u hat, if you recall from reciprocal theorem, I will not spend this too much time, but I will just show what this is. So, sigma hat is minus p hat delta plus 2 mu E hat. Now, sigma is symmetric, del u is made up of both symmetric and antisymmetric, but I do not need to carry the antisymmetric part along, right. So, I will only carry the symmetric part. Now, what is the first term? Minus p So, this one is one sec, let me just make sure I have kept the tensorial order correct. So, this is supposed to be, where was it? This is supposed to be a double dot product. So, what is the first term? What is delta double dotted with E? Delta ij Eij, which is Eii, which is 0 because of incompressibility. So, this term is 2 mu right, and similarly you will get the same term from also the last part. So, they are going to cancel each other. So, with all that you will now have, let me write the expression. So, there are only two non-zero terms, there is this one and there is this particular part. Now, the sigma 1 dot n ds, what is this quantity? It is the force acting on the fluid, the negative sign gives me the force acting on the particle. So, Ey dot F will be force along the y direction or the lift force. So, the lift force is going to be divergence of sigma 1 dot u hat dV. What is divergence of sigma hat? The body force F. What is the body force F? This entire right hand side. So, finally, what you get is the lift force is u hat u infinity dot del u 0 dot del u infinity plus u 0 dot del u 0 dV. That is the lift force that it experiences. Now, why is it I have made a big deal of this calculation? What is the part of this calculation that is really remarkable? What do you need to do this volume integral? What quantities do you need? U infinity is given. What do you need to find? You need to find two problems, right? What are these two problems? They are Stokes flow problems. They are homogeneous Stokes flow problems. So, you solve for the Stokes flow problem of a spherical particle in a quiescent fluid between two plates moving towards the wall, which is the test problem, and you solve the other problem which is in a channel flow. There is a spherical particle that is force free and torque free. Both are Stokes flow problems, and using these Stokes flow problems you do one volume integral and compute what the force the particle experiences. So, that is the part which is remarkable in this entire exercise, that you did not actually have to solve for anything specific to finite inertia. You only solved for, so this is why reciprocal theorem is often labeled as pulling something out of a magic hat, because you did not do any calculation at finite Reynolds number. You are only doing Stokes flow problem, but by rightly identifying the necessary Stokes flow problem, you have managed to find something which is a very remarkably inertial effect, that particles will not stay on the streamline where they are initially introduced, they are going to migrate. So, this exercise, the reason why I spent a little bit of time is, you see now actually an application of reciprocal theorem that is more or less at the frontier of how you do these calculation. Now, why is inertial migration something that is a big deal? I mean, you will, if you search around, you will find that there are tons of paper which continuously keep coming out on inertial migration. The reason this becomes so interesting is you can use these inertial forces to segregate particles. You are not putting any manual filter, you are not trying to drag them. So, if you have to sort particles, and this becomes quite important when you are thinking in terms of biological problems, you want to sort particles, you are using hydrodynamic effects in order to segregate particles. So, if you had a channel where there were bigger and smaller particles which were present, there was a mixture of big particles and small particles. Again, in the biological problem, you can think of two different size of cells that are there. If it was Stokes flow, they will all stay together in that mixed, jumbled up state. But if you rightly choose the value of Reynolds number, you can make them segregate, where you will find that the bigger ones are going to cluster at one location, the smaller ones will cluster at some other location. You can do this natural segregation, and then you can create, let us say, a bifurcation of this channel, and you can filter them out, and you have managed to do all of this without putting any mechanical sorter or doing some electric effect or doing some magnetic effect or doing some other kind of effects where you are invasively trying to separate them. This is a completely non-invasive way by which you can segregate objects purely using hydrodynamic forces. Because if you remember, in our early discussion we had that the scaling for the lift force would be, if you take the load Reynolds number behavior, load Reynolds number tells us that mu u, this is our characteristic velocity, mu u times a, that is the scale of force in low Reynolds number, but this is a finite Reynolds effect, which means this is multiplied by a Reynolds number. Now what is this? This is gamma dot A square by nu, which means mu by nu is, what is mu by nu? Density, right, this is rho. So this is rho gamma dot square A to the power 4, right. So if you are thinking of large particle with particle size, I mean I am trying to simplify this because there will be a non-dimensional function of A by h also which will appear here, where it is located, etc. But the point I am making here is that with particle size it scales with the 4th power, which means if you have particles which have roughly a 50% contrast in size, the difference in force will be 6 times larger, right. You can really use this very effectively in segregating them, and obviously if you know the force you can also find the vertical velocity, which is force by resistance or force by mobility. For a problem in, if you think of it like an unbounded problem, you divide it by 6 pi mu a, it gives you the migration velocity. So somewhere the force will vanish. So the location where the force vanishes is where it will go and sit. So now you can think that they are going to constantly experience force, and at some location the force is going to go to 0. So where the force goes to 0 is where finally they will equilibrate. So this is one very interesting application of finite but small Reynolds number effect going from Stokes flow, and you can see that you have done only Stokes flow problem, you can do all of that and still manage to actually compute what would be the lift force or the migration velocity or the equilibrium location for this kind of a configuration without doing any finite Reynolds number calculation by using reciprocal theorem. Obviously this is only applicable when the walls of the channel are lying within the Eocene region, otherwise you will have to do something else. Okay. So with this I will end today's discussion. So this is primarily where we end the other axis. We still have a third axis to discuss, which I will take up in the next lecture. So we have discussed things which are going on in the axis moving with Stokes. We have discussed a little bit of what goes along the axis with Reynolds, but this is right now still an unknown thing, and that is what we will touch upon in the next lecture. Okay, thank you.